Great. Hello, everyone. Very happy to be here. I'm not sure if we have a moderator with us, but let's just go ahead and start. So I'm Magdalena Stenius, and my topic for today is understanding the carbon footprint of machine learning. And I'm super excited to be part of Confer. Big thanks to Rustam and the other organizers for pulling this together. So a little bit about the background of why I'm giving this talk today. I've grown up in the early 2000s in Helsinki in Finland. And when I went to school, part of our upbringing was the environmental aspect of realizing that we're really living in a planet that is already overconsumed. We are kind of already in a bad situation. And in school, we were always taught to, for example, not waste water. We should close the tap after having enough water, and we would always recycle our waste. We would also always be instructed to turn off the lights when we were leaving a room. There was a heavy focus on really making even children aware of these issues and kind of showing the children as well how to change the situation we are in. And now my generation has grown up and we're entering the workforce. And one part of that is that we want to bring part of this upbringing with us to whatever fields we're working in right now. According to MIT's technology review, some of these deep learning models that we're using today, especially natural language processing models, a training of one of these models can consume up to the same amount of carbon dioxide equivalent that 5 cars would produce during their entire lifetime. Here are some of the examples of these natural language processing models and their trainings, and how large their carbon footprints are. If you want a little bit of context for this, the average household in the US would produce about 48,000 kilograms of CO2 equivalent per year. So these numbers are exceeding even those. And as you can see, right next to the carbon footprint, there's also the cloud compute cost of one of these model trainings. And this is maybe my second message to those of you who are listening, who are maybe business decision makers or in an executive role in a company. If you're not passionate about saving the planet or the green movement, then at least you can be passionate about saving money. And that's really a large part of green software and the whole trend of making software and machine learning projects more environmentally friendly. So nice to meet all of you. You can find me on GitHub. My nick is Magda Poppins. I work as a machine learning engineer at the machine learning operations platform Valohai. And I'm a cat person. I even have a cat behind my computer screen right now as I'm talking. And I'm super happy to meet new people. So come say hi, for example, on LinkedIn. I'm happy to connect. The agenda for this talk will be to first look a little bit about the background, why we grew interested in measuring the carbon emissions of machine learning models. Then we will take a glance at the journey of finding some of these estimates and really the methodology of estimating carbon emissions of a product. And lastly, we will also glance into moving forward and kind of what the next steps in this field really would be. This was an article published in Helsingin Sanomat, which is the largest Finnish newsletter, just a few days ago. For those of you who don't know Finnish, the title is Green Code, and the whole article is about how this large Finnish bus company, Matkahuolto, reduced their carbon emissions significantly and also saved thousands of euros per just measuring their infrastructure usage and reducing these unused resources, cloud resources. And this is really a trend that we see going on and becoming more and more prevalent nowadays. So some call it green code, some call it green software. And some of the themes that have risen in this topic have been, for example, the optimizing of code and infrastructure usage. I know, for example, also the Finnish news, the government's news agency, Yle, has done some amazing work with measuring the carbon footprints of their infrastructure usage and using that as a motivator to reduce unused resources and really optimize those the cloud resources they have at hand. Another topic has been the choice of programming language. For example, we have seen some comparisons between languages such as C, which are very low level and consume very little electricity, compared to, for example, Python, which is, again, like a more electricity heavy programming language. And then we also have seen some nice takes on reducing the carbon footprint of web applications. The most used methodology in this has traditionally been minimizing the transfer data. There are some services that are offering measurings of carbon footprints of websites, and they always seem to rely on how large these packages or the files sent in the website are, as well as how many daily active users the website has. So then moving on to the context of machine learning. And for those of us who work with machine learning, we can recognize the specialty of this field or software with machine learning aspects. One of the specialties is definitely the compute-intensive work of training these machine learning models. So if you're not familiar with machine learning models and how they're functioning, they are basically mathematical functions where you have data woven into the functionality of the model. And this training of the model, so to speak, is what takes a lot of compute, especially when you're talking about these deep learning models, such as these deep neural networks used for example, generating new text. Machine learning also has some specific hardware requirements. So usually would use some hardware that you don't need in general computer science. One of these are the specific accelerators, for example, GPUs. But then on the other hand, there's also similarities to software projects. For example, model consumption can be basically done just over an inference endpoint, which is just over HTTP. Another kind of specialty of machine learning is the massive data sets. And also the topic of minimal models or models living on edge devices has become increasingly prominent. So why we took interest in this topic, as I said, is that we are a machine learning platform. So we offer data scientists the tools they need for training machine learning models. And we do have a lot of customers running their trainings on our platform, amounting up to over 100,000 machine learning models trained on our platform each month. This is only the cloud that we vendor. Then, of course, we also have some customers with on-premise installations that are not included in this number. And our customers mostly go for the three big cloud providers, AWS, Azure, and Google Cloud Compute. So our first challenge was, since all of our customers or almost all of our customers are using cloud providers, can't we just easily access this information in the cloud providers' APIs? For example, AWS has just recently launched their carbon emissions footprint tool. And we see similar initiatives also coming from Azure and from Google Cloud, where the cloud providers themselves are offering to tell customers how much their carbon footprint has been for a specific amount of time. This is the AWS's kind of sales picture for this feature. And I was very excited because I'm interested in this topic. Our AWS bills are massive. Most of our own infrastructure is hosted on AWS. And I was really excited to see what kind of carbon emissions we are amounting to. So the excitement was high when I opened the view in our billing console, and it looked like this. Apparently, we have had some carbon emissions in 2020, and they have stopped in 2021. And after that, we have had none whatsoever carbon emissions on our platform. When I first saw this, I was really confused. I was sure that maybe because this feature is still in beta, it's not maybe reliable and there's some kind of bug. But when I researched the matter a bit further, I found out that AWS actually doesn't report carbon emissions from carbon compensated regions. So they have this methodology of compensating from carbon emissions where they pump renewable energy into the grid to compensate for the non-renewable energy they used. And all of our infrastructure happens to be in EU West 1, which is one of these carbon compensated regions. So effectively, it looks like we don't have any emissions at all from our platform. Of course, this is not the whole truth. There are emissions, but for mainly business reasons, AWS is choosing not to report them and showing them as carbon compensated. And this is the challenge with this cloud provider's own APIs. They have a business incentive of showing this data, and they don't want those numbers to look bad. Well, kind of the tip you could draw from this is use cloud compensated compute, carbon compensated compute. So if you are on AWS, for example, look for those regions where the electricity is compensated with renewable energy. But this was not enough for us. We headed onto a journey for looking at more under the hood, what are the carbon emissions of compute and how we could understand this topic a little bit better than these cloud provider APIs can tell. So when we're talking about cloud or greenhouse emissions, we can use this model called the GHG protocol. The GHG protocol divides emissions into 3 different scopes. Scope 1 being the direct emissions of the company that's being reported. Scope 2 being the indirect emissions of the electricity consumed. And Scope 3 being, for example, the manufacturing emissions of the actual tools used by that company. So if we look into these 3 scopes from a data center vendor's perspective, Scope 1 would be the natural gas and diesel that are consumed by this data center. Scope 2 would be the purchased electricity into the data center. And Scope 3 would be the server hardware manufacturing and constructions of that data center. So let's start at looking at the Scope 2 of this way of measuring at the electricity consumed by the data center. Compute electricity is mainly impacted by the processor load and memory usage of an application. And what else matters when measuring the electricity of especially data centers is that the region in which the data center is located in, as well as the data center setup, really matters. So one of the classical tips is, of course, optimize your code so we can get that processor load and memory usage as down as possible. But then let's move on to look a little bit at the data center's perspective of electricity. For this, we have a useful term called PUE, or power usage effectiveness, which is used to describe the effectiveness of power usage in a data center. The PUE value is built upon the total power coming in, and that's relation to the percentage of that power going to servers. So we can think of data centers as being more efficient when more of the electricity coming in is going directly to power the servers and less electricity is needed, for example, for cooling. When we're measuring that PUE, or power usage effectiveness, we take the total power going into the data center and divide that by the total power used by the servers. And the optimal value in this case is 1. So we would like for all of the electricity going into the data center to be used directly by the computers or the servers. And in this matter, using cloud compute really does matter, and especially hyperscale cloud compute. The average data center PUE in the United States is around 1.7, whereas, for example, Google reports as impressive numbers as 1.12. So you can see that we can really reduce our electricity carbon emissions drastically by selecting these hyperscale cloud vendors over owned data centers, just because they are able to, because of the massive scale, build those data centers in a much more efficient way. So that's my third tip: use cloud compute if possible. And then moving on to the electricity carbon intensity. So that's another term that is kind of useful in this context. The carbon intensity of electricity basically means how many grams of CO2 is released when we produce, for example, 1 kilowatt hour. And this really does vary according to region a lot. So here we can have, we can see a map of the regions where basically this cloud or the electricity carbon intensity is varying. If you're located in Europe and if you want to have your data centers or your data usage somewhere in Europe, we would always recommend to choose the regions that are low in carbon intensity. So basically, that's mostly the Nordics, especially Sweden and Norway stand out as very efficient countries in this way. So that's my fourth tip. When you're using cloud compute, do look at the regions you're using and do choose those cleaner regions. You can find data on this, for example, on this ourworldindata.org. Also, Cloud Carbon Footprint has a nice initiative about this. So this is really an easy way to kind of impact your carbon footprint. So then, how much electricity is the machine actually consuming? The next challenge we ran into was kind of the naive idea of, can't we just ask the machines how much they consume? Because, for example, if we have a Mac computer, we can use applications such as Stat to see our current electricity or an estimation of our system total power usage at a given time. The challenge we ran into here was that virtualization kind of blurs out the border between hardware and kind of the actual machine. And we found an amazing resource related to this gathered by Teach Engineering, and especially in the regard to AWS EC2 compute. So what Teach Engineering had done with this in this field was that they found that AWS instances are virtualized in such a way that they can be directly mapped to the hardware. A specific hardware is always allocated to a specific instance. And their sizing is also kind of mappable in a way that, for example, a P3.8x large is half of the resources, the physical resources of a P3 16x large, etc. Knowing this, they used tools such as Turbostat on AWS bare metal instances to find electricity consumption at various load levels. Because contrary to regular AWS instances, bare metal instances actually do expose some of these informations to the user. From that, from those results, they were then able to map the resource usage into the virtualized resources and then generalize them to other instance types. If you're interested in this, they have an awesome blog post series on this topic, which is actually a really interesting read. So I do encourage you to find that and look it up and read through it, because it's mind-blowing. So here is the resulting open source dataset. It's licensed under Creative Commons, and it's available for everyone to see. And you can find all the different AWS instance types and their electricity consumption at various load levels here. So now that we dealt with the electricity the machine is consuming while the training has been run, let's look at the manufacturing part of the emissions. According to Udit Gupta and others, the majority of data center emissions actually come from hardware manufacturing. The challenge in this is that we would like to find the emissions per component in the manufactured devices. Related to this, there's an awesome initiative called the Boa Vista Hardware Emissions Dataset, where Boa Vista is gathering data from different hardware manufacturers to kind of calculate the emissions of these different types of hardware. And I really would encourage you to look at this project and, if possible, also contribute to it in a way that we could have more information on, for example, server manufacturing emissions later down the road. So let's again look at the Teach Engineering EC2 dataset. They have this way of defining the manufacturing emissions that builds upon this methodology where you would have assumed a minimal rack server setup that has the emissions of, that has 1,000 kilograms of CO2 equivalent emissions. From that minimal rack server, you would start building up, depending a lot on which kind of hardware that specific instance type has. So there were defined some arbitrary emissions for extra hardware, CPUs, GPUs, dynamic random access memory, hard disk drives, and solid state drives. Now let's look at an example of a concrete machine instance type on AWS. For example, the P4D 24x large, which is commonly used in machine learning because it belongs to this accelerated computing family. The minimal rack server is there, 1,000 kilograms of CO2 equivalent. In addition, we have totally 96 virtual CPUs. And looking at the CPU processor model that we have in that specific instance, which AWS exposes, we find that it's a Xeon Platinum processor, which can multi-thread up to 48 threads at the same time. From there, we can deduct that there are two actual processor or CPUs on that machine. So that means one above the minimal rack server. So we add the amount of one extra CPU. We also look at the memory. So we can see that there is some extra memory, and we calculate the emissions for that specific amount of extra memory. We also find 8 NVIDIA GPUs and add that just directly from the naive 150 kilos of CO2 equivalent per GPU. And then we have some extra storage. So from this, we can find that the total manufacturing emissions of this type of machine amounts to 4,778 kilograms of CO2 equivalent. And keep in mind that this machine can then be used over a span of 4 years approximately. So the last challenge we faced was accepting the imperfection of all the methodology related to estimating carbon emissions. As engineers, it's really hard for us to accept that it's not always completely clear how many grams a certain amount of processors or a certain amount of GPUs are amounting to. There's a lot of fuzziness in this whole field, and a big shout out really to, for example, initiatives like the Boa Vista initiative and Teach Engineering for tackling those challenges, although there are a lot of maybes and insecurities in the field. But we decided to use the tools that we found and build our own open-sourced Python package for calculating the emissions of machine learning trainings ran on AWS instances based on this data that we found. So here is the result. For each machine learning training we run, you can now see an estimation of the emissions. This is, of course, optional to look at, but it's a bit interesting. And here you can see a division of the Scope 2 emissions, Scope 3 emissions, the license of the data. So, for example, in this case, it's based on the Teach Engineering dataset. And you can also see details on whether or not this compute was in some way compensated. One of the questions that remained unanswered after this attempt of ours was the emissions of object storage. In Valohai, we rely heavily on S3 storage and S3 kind of fitting storage types. And contrary to compute services, AWS doesn't expose any of these internals of these storage services. However, if we look at the energy consumption of compute and compare that to the energy consumption of storage, storage takes actually relatively little energy. So 1 terabyte of solid-state drive storage takes on average only about 2.2 watts per hour, compared to, for example, the machine that we looked at before, which takes up to 3,782 watts per hour. So we can perhaps hope that based on this, the actual emissions of storing data wouldn't be that large. Of course, this means the data is in a resting state. So immediately when we are accessing it, reading and writing, then that again, of course, is a new challenge. Here is the resulting, or the README of the resulting GitHub project. So you can find this on GitHub. It's, as I said, it's open source. It's freely usable by anyone. You can also just directly install it using pip. And if you're using AWS instances for compute, whether it be machine learning or anything else, you can use the package to get an estimate of your emissions. And lastly, what's next? A big trend that I see in this field is estimating the emissions beyond greenhouse gas. So especially when it comes to component manufacturing, greenhouse gas emissions are just not enough to measure really, for example, the minerals and raw materials emissions used in that manufacturing process. So I'd like to see a development of even further methodology of estimating kind of the complete emissions of different products. And related to this, I would love to see the Boa Vista manufacturing emissions dataset flourish. I hope this is a trend that will become more and more prevalent. People are starting to ask for the emissions of different kinds of technical devices, including also, of course, servers and rack servers. So I would love to see more transparency in that field, and especially now from the cloud providers who are the direct consumers of these kind of rack servers, to really more openly talk about where they buy these products from, what the emissions are, so we don't need to do a lot of detective work and guessing. And also, I'd like to see more standard procedures related to carbon compensation. So for example, also Google Cloud has some really big kind of compensation systems in place. As I mentioned before, AWS also does this. So instead of just seeing that you have zero emissions because we compensated them behind the scenes, I would really like for these cloud providers to now open up about what the different methodologies are behind these compensations, why they have chosen this method of compensating the carbon emissions, and what kind of impact does it really have in that direct region where this compute is happening. So that was all I had today. Thank you so much for listening in. And I'm really happy, as I said, to meet new people. So feel free to reach out, give me some feedback on my talk, and talk more. So thanks on my behalf. And let's see. Great. I don't see any questions either. So I will just go ahead and wrap up. So thanks once more.